Welcome everyone. For today's prep, we're going to start to look at constrained optimization. So we're going to see what this special type of problem is. And well, we're going to see how we can use derivatives to help us solve these. So we're going to look at just this first example here. And this kind of gives us an idea of the overall strategy we're going to be using and what exactly these types of problems actually are. So let's look at example 1. And we have this statement. It's asking us to do something. We want to find the maximum value of this expression q equal to x times y. And we have this extra condition that x plus y must be equal to 2. So we want to maximize this expression. And the right side of this expression is a two-variable function. So it has both x's and y's on it, or sometimes we might be using other variables, but in this case we're using x's and y's. So this is a two-variable function over here. And we have this kind of this extra condition. So we're going to see what kind of these two equations are doing. And this is really the setup for what a constrained optimization problem is going to look like. We're going to have these two kind of expressions, and we're going to kind of use them together. All right, so we want to find the maximum value of this two-variable function here. Now, so far, we've only been able to do derivatives of one-variable functions. So what are we going to do with this two-variable function? Well, that's where this other expression is going to come in. So our first step is we're going to determine what's called the objective and the constraint equations. So the objective equation is whatever we want to maximize or minimize. So in this case, if we're kind of reading through, we want to find the maximum value of this. So this is the expression that we want to maximize. So that's going to be our objective. Okay. And then the constraint equation, this is our second type of equation. And this is some other information that we're given that puts some restriction on our variables. So in this case, we want to maximize this function, this expression, but x and y just can't be anything. They have to satisfy this equation as well. So x plus y must be equal to 2 in this case. So we can't just have any x's and y's. Otherwise, we could just make this number really big, or make our numbers really big and make it as big as we want. We have some kind of limitation here. X plus y must be equal to 2. So that's our constraint. We're limited. Okay, so we have our objective. And we have our constraint. So step 2, once we've identified those, step 2 is we're going to first start working with this constraint equation, and we're going to solve it for one of the variables. So we have a choice. Just pick whichever variable is easier to solve for. So in this case, it doesn't really matter. So our constraint equation is x plus y equal to 2. And just for familiarity's sake, let's just solve for y. But really, I could have just as easily solved for x here. So if we solve for y, we get y is equal to 2 minus x. So I'm just going to move that x to the other side. All right, so now we've worked with our constraint. So step 3 then is we're going to take this value for y that we just found, and we're going to plug it into our objective. And this is going to give us a one-variable function that we can optimize then. So our objective is q equal to x times y. That was our objective. And we're going to plug in that constraint. So in our case, we found that y was equal to 2 minus x. So wherever I see a y in my objective equation here, my objective function, I'm going to switch that over to a 2 minus x. So I'm going to have the x that's there, and then I'm changing this y to 2 minus x. Now, why is that important? Well, this now is a one variable function. So we have all of our techniques that we've spent in the weeks looking at for how to optimize, find the max or the min for a one variable function. And we know that this is going to involve doing derivatives. So to help make the derivative easier, let's actually multiply this out. So when we do that, we get 2x minus x squared. All right, so now we do the calculus. So far there's not been any calculus. We're going to optimize this function, and this is where we get going. So first part of this is we want to find our critical numbers. So if we remember, the critical numbers, that's where our function might have a max or a min. Those are the only places where our function might have a max or a min. And the way we find our critical numbers is we do the derivative, and then we figure out where the derivative is 0 or undefined. So let's calculate our derivative. So I'll call it q prime. And if we differentiate, we get 2 minus 2x. So there's our derivative. And then we just want to figure out, where is this derivative 0? Where is it undefined? So we want to know, when is our derivative 0? In which case, if we set 2 minus 2x equal to 0 and solve, we get x equal to 1. And similar, if we look at where our derivative is undefined, well, our derivative here is 2 minus 2x. So really, we've seen this before. The only times we really run into issues normally is if we have a fraction here, if we have a negative exponent. We don't have any of that. So there's no places where our derivative is undefined. All right, so we got one critical number, x equal to 1. And the second part of our calculus work here is to classify. And we've learned two tests that we can use to figure out if a critical number is a max or a min. And normally the quickest one is the second derivative test. So let's try that first. And whenever we try out a test, let's write the name. So we're doing the second derivative test. So as the name suggests, we got to calculate our second derivative. So we'll calculate q double prime. Differentiate this, we get negative 2. And the way we do our second derivative test is we take the critical number that we're interested in classifying and we plug it into our second derivative. So we're going to plug in x equals 1 into our second derivative function here. Now this second derivative is just a constant. So in this case, when I plug x equals 1 in, I end up getting negative 2. And if we remember what our second derivative test says, it relates us to concavity. So we really just care that this is a negative. Negative second derivative means concave down. To help us remember the test, draw the concave down shape, and we see that we do have a max. So our function here has and let me move. Our function does have a local max at x equals 1. And actually, we found only one critical number. So not only is this a local max, it's the absolute max. So we found one critical number, which implies that we actually have an absolute max at x equals 1. And that's it. We've basically done the hard work here. So we've figured out where we have a max, and we did verify that we actually do have a max there. All right, so the last step then, step 5, is to just make sure that we actually answer the question. So let's go back to the question. What did it say? Well, it said to find the max value of this expression. So we found that we have a maximum at x equals 1, but the question's actually asking us to get the max value of that function. So we just want to make sure, sometimes the directions might say find the x value or find the y value. In this case, it's saying find the value of our function here. So we could go back and figure out what y is when x is equal to 1. And then once we have x and y, we could then plug both of them into that function. But to kind of save a step, we also have this one variable version of q that we could just plug into as well. So let's do that. So it's actually asking for the q value here. And so when we plug in, we're going to plug x equals 1 into our q function, and there it is. So we get 2 times 1 minus 1 squared, which is just 1. So there we go. We've actually answered the question. And this is really the idea. These are going to be the steps that we take. So, as we get a little more practice, the types of equations and the calculus that goes into this is going to be a little bit more complicated. But essentially, we're going to be following these same steps throughout. All right, so we'll get a little more practice in class. So we'll see you then. Bye-bye.